For decades, humanity has pointed its telescopes toward the stars, expecting to find signs that we are not alone. The universe contains hundreds of billions of galaxies, trillions of planets, and countless opportunities for life to emerge. Yet everywhere scientists look, they find the same unsettling result: silence. Tonight we explore one of the greatest mysteries in science, the Great Silence. Why does a universe so vast appear so empty? Are intelligent civilizations incredibly rare? Have they vanished before reaching the stars? Or is there something about the cosmos that makes contact far more difficult than anyone imagined? If fascinating journeys through space science and the deepest mysteries of the universe help make evenings more relaxing, be sure to like this video, subscribe to the channel, and join us for more cosmic bedtime stories. Now, as the stars slowly fill the darkness above, let the journey begin. The universe at its largest observable scale presents a structure defined less by what is present and more by what is absent. Vast regions of space stretch between concentrations of matter, forming enormous voids where galaxies are rare and light travels through near emptiness. These voids are not empty in an absolute sense, yet their density of particles is so low that they behave like almost complete silence in physical terms. Matter exists primarily along thin interconnected strands known as cosmic filaments, where gravity has slowly gathered gas dust and galaxies over billions of years. Between these filaments, space expands into regions so sparse that a single hydrogen atom may occupy volumes comparable to entire planetary systems. This imbalance between structure and emptiness forms the foundation of a large-scale cosmic architecture. In these void regions, gravitational influence is weak, and the formation of new galaxies is extremely limited. The expansion of the universe stretches these underdense areas further apart over time, causing them to grow larger and more isolated. Light passing through such regions encounters almost no scattering material, allowing it to travel vast distances without significant interruption. Yet this clarity does not translate into activity. Instead, it reinforces the impression of silence, as energetic events are rare and widely separated in both space and time. Any radiation emitted from distant structures fades gradually into background levels long before reaching other dense regions. The cosmic voids themselves are shaped by early conditions in the universe, when small fluctuations in density determined where matter would eventually gather. Over time, gravity amplified these tiny differences, pulling matter toward denser regions, while leaving behind increasingly empty expanses. This process created a foam-like structure, on the larger scales often described as the cosmic web. The voids are the open spaces within this web, expanding as surrounding filaments grow thicker and more defined. Within these regions, temperature and pressure conditions are so low that conventional chemistry becomes nearly irrelevant, and interactions between particles are extremely infrequent. Despite their emptiness, cosmic voids are not static. They expand as the universe expands, and their internal conditions evolve slowly over time. Sparse particles drift through them, occasionally influenced by distant gravitational fields, but collisions are so rare that long-term interactions are effectively negligible. In this environment, the usual drivers of complexity, pressure, density, and frequent interaction are absent. Without these factors, matter remains diffuse and inactive, contributing to the overall impression of a quiet and undisturbed cosmic background. The distribution of matter around these voids plays a crucial role in shaping observable structure. Galaxies along filaments act as boundary markers outlining the edges of emptiness with luminous clusters. These clusters contain billions of stars, yet their separation from other clusters is immense, reinforcing the contrast between density and isolation. As light emerges from these regions, it traverses voids, that contain little to alter its path, preserving its trajectory across billions of years. This journey through near-nothingness highlights the scale of separation between active regions of the universe. Within the voids, gravitational potentials are shallow, meaning there is little tendency for matter to accumulate or collapse. Any small concentration of gas tends to disperse rather than condense, preventing the formation of new stars or galaxies. Over cosmic timescales, this reinforces the emptiness as material gradually drains toward denser structures at the boundaries. The result is a self-reinforcing separation between active and inactive regions of space, where activity becomes concentrated and silence expands outward. Although voids are often described as empty, they still contain traces of the intergalactic medium primarily composed of hydrogen and helium left over from the early universe. This gas exists at extremely low densities and temperatures often close to absolute minimum conditions permitted by cosmic background radiation. In such states, chemical reactions are extremely rare, and ionization states remain stable over long durations. The presence of this faint medium ensures that voids are not truly devoid of matter, but rather represent the lowest density environments known on cosmic scales. The perception of silence in these regions is not auditory but structural. It emerges from the absence of energetic interactions that produce observable signals. Without frequent star formation, supernova activity, or galactic collisions, there is little to generate strong emissions. As a result, cosmic voids contribute to a universe where most detectable events are confined to dense regions, while vast expanses remain comparatively inactive. This imbalance shapes the overall observational landscape, where most signals originate from narrow regions embedded within overwhelming emptiness. Over time, the expansion of space continues to increase the scale of these voids. As distances grow, communication between distant regions becomes progressively more limited, not because signals cease to exist, but because they are stretched and diluted by expansion. This effect enhances the sense of separation, reinforcing the structural quietness of the large-scale universe. The voids therefore function as both physical and observational barriers, shaping how matter and radiation are distributed across cosmic history. At this larger scale, the universe presents a framework where structure and silence are interdependent. Dense filaments define where activity occurs, while voids define where it does not. This duality establishes a balance in which most of space is inactive and only limited regions host energetic processes. The result is a cosmos that appears active in localized areas, yet overwhelmingly quiet when viewed as a whole, with emptiness dominating the overall architecture. Beyond the vast voids of the cosmic landscape, matter gathers into elongated structures known as galactic filaments, forming a connected network that spans the observable universe. These filaments are not solid objects, but diffuse bridges composed of dark matter gas and embedded galaxies shaped over billions of years by gravity. Their formation begins with small density variations in the early universe, where slightly denser regions attract surrounding material. As this process continues, matter flows along invisible gravitational pathways, gradually forming extended structures that link clusters of galaxies together. These structures define the boundaries of emptiness, giving shape to the large-scale cosmic web. Within these filaments, galaxies are distributed unevenly, often grouped into clusters separated by vast distances. Each cluster contains hundreds or thousands of galaxies, bound together by gravity, yet even within these dense regions the distances between individual galaxies remain enormous. The filaments themselves act as highways of matter, slowly channeling gas and dust toward gravitational wells, where galaxies form and evolve. This continuous but extremely slow movement of material contributes to a universe where structure exists, but interaction remains limited by scale. Dark matter plays a central role in maintaining the integrity of these filaments. Although it does not emit or absorb light, its gravitational influence shapes the distribution of visible matter. Observations indicate that dark matter forms a scaffolding that guides the formation of galaxies, allowing baryonic matter to accumulate along its structure. This hidden framework is essential for explaining why galaxies appear aligned along filamentary paths rather than distributed randomly. The presence of dark matter ensures that large-scale structure remains stable over cosmic time even as the universe expands. Despite their size and mass, galactic filaments are extremely diffuse compared to structures on smaller scales. The gas within them exists at low density and high temperature, often ionized due to exposure to background radiation and shock heating from gravitational collapse. In these conditions, atoms rarely interact and energy exchange occurs slowly. This leads to an environment where matter is present but not actively engaged in rapid transformation. The filaments, therefore, represent a transitional state between the emptiness of voids and the concentrated activity of galaxies. At the intersections of filaments, galaxy clusters form where gravitational attraction is strongest. These nodes contain hot gas that emits X-rays, revealing energetic environments shaped by repeated mergers and interactions. However, even these active regions are separated by immense stretches of near emptiness, reinforcing the contrast between localized complexity and large-scale silence. The clusters act as focal points of cosmic activity, yet their influence diminishes rapidly with distance, leaving surrounding space largely unaffected. Matter flowing through filaments does so over extremely long timescales. Gas slowly moves along gravitational gradients, accumulating in denser regions, where it may eventually contribute to star formation. This process is gradual and inefficient compared to chemical or physical processes on planetary scales. The slow nature of this movement contributes to the perception of a quiet universe, where changes occur but only across spans of time far beyond human experience. The structure of filaments is not static. Over billions of years they evolve as gravity pulls matter inward, and cosmic expansion stretches their outer regions. Some filaments grow thicker as they accumulate more galaxies, while others become thinner and eventually disconnect from larger networks. This dynamic evolution reflects the ongoing competition between gravitational attraction and cosmic expansion. Despite this evolution, the overall pattern of the cosmic web remains stable in its large-scale appearance, with interconnected strands persisting across time. Radiation traveling through these filaments interacts weakly with the sparse gas present. Light from distant galaxies may pass through multiple filaments before reaching observers, yet the low density of matter means that absorption and scattering are minimal. This allows observations of extremely distant objects, but it also highlights the lack of intervening activity. The journey of light across these regions emphasizes the quiet nature of intergalactic space, where energetic processes are rare and widely separated. Within the filaments, small-scale turbulence can occur where gas is compressed or heated by gravitational forces. These localized disturbances can briefly increase temperature and density, but they remain isolated events within a broader context of stability. Such fluctuations are insufficient to significantly alter the overall structure of the filament network. Instead, they dissipate over time, returning the system to a state of equilibrium shaped by large-scale gravitational forces. The distribution of galaxies along filaments also influences how the universe is observed. From any given point, most visible structures lie along specific directions defined by these cosmic pathways. Between these directions, vast regions of sky appear relatively empty, reinforcing the impression of uneven structure. This anisotropy reflects the underlying filamentary architecture where matter is concentrated in narrow regions rather than spread uniformly. As the universe continues to expand, the separation between filaments increases. Some structures become increasingly isolated from one another, reducing the likelihood of interaction between distant clusters. This expansion contributes to the long-term trend toward increased cosmic quietness, as regions of activity become more separated in both space and time. Over extremely long periods, some filaments may become gravitationally unbound from each other, further emphasizing the fragmentation of large-scale structure. At this scale, the universe appears as a network of connected but distant regions of matter, surrounded by vast empty spaces. The filaments themselves represent the pathways of cosmic evolution, yet they occupy only a small fraction of the total volume of space. The overwhelming majority of the universe remains unoccupied by dense structures, reinforcing the dominance of emptiness in the overall cosmic composition. Between the large-scale filaments of galaxies lies the intergalactic medium, a diffuse collection of gas that fills the spaces separating all major cosmic structures. This medium is composed primarily of hydrogen and helium, the simplest and most abundant elements formed in the early universe. Although it spans the entirety of intergalactic space, its density is extremely low, often far below any vacuum achievable on Earth. The particles within it are separated by distances so vast that collisions occur only rarely, making it one of the most inactive environments in existence. The intergalactic medium exists in a state shaped by both primordial conditions and ongoing cosmic processes. In the aftermath of the early expansion of the universe, matter was distributed unevenly, leaving behind regions of varying density. Over time, gravitational forces drew much of this matter into galaxies and filaments, but a significant fraction remained spread across intergalactic space. This residual gas forms a faint background that permeates all large-scale structures, acting as a silent reservoir of baryonic matter that is not bound to galaxies. Despite its low density, the intergalactic medium is not uniform. In some regions, particularly near galaxy clusters and filaments, it becomes slightly denser and hotter due to gravitational compression and shock heating. In other regions, especially within cosmic voids, it becomes even more rarefied and cooler. These variations create subtle gradients across vast distances, yet even the densest parts of this medium remain extremely thin compared to any planetary atmosphere. The differences are measurable only through highly sensitive astronomical observations. The temperature of the intergalactic medium varies widely depending on its location and history. In regions influenced by energetic processes such as galaxy formation or supernova-driven outflows, the gas can reach temperatures of millions of degrees. In contrast, more isolated regions remain much cooler, though still influenced by the background radiation of the universe. Despite these high temperatures, in some areas the low density prevents the gas from behaving like a conventional hot environment. Instead, it remains tenuous, with particles moving freely over long distances without frequent interaction. Ionization is a key feature of the intergalactic medium. Much of the gas exists in a state where electrons are separated from atomic nuclei, forming a plasma. This ionization is maintained by ultraviolet background radiation, produced by galaxies and quasars. As a result, the medium remains electrically active on a microscopic level, yet this activity does not translate into large-scale energetic events. The plasma behaves in a smooth and diffuse manner, lacking the turbulence seen in denser astrophysical environments. Light traveling through the intergalactic medium experiences minimal obstruction. Photons emitted from distant galaxies can traverse billions of light-years with only slight absorption or scattering. However, subtle interactions do occur, such as the absorption of specific wavelengths by neutral hydrogen, creating faint signatures in the spectra of distant objects. These signatures allow astronomers to study the composition and distribution of intergalactic gas, revealing the structure of otherwise invisible matter. The intergalactic medium also plays a role in the exchange of matter between galaxies and their surroundings. Galactic winds driven by supernovae and active galactic nuclei can expel gas into intergalactic space, enriching it with heavier elements. These elements then disperse slowly across vast distances, mixing with primordial hydrogen and helium. Despite this exchange, the overall rate of mixing is extremely slow, and chemical evolution in this environment proceeds on timescales far longer than those typical of galactic interiors. In regions where gas flows along filaments, the intergalactic medium becomes slightly more dynamic. Matter gradually moves toward gravitational wells, contributing to the growth of galaxies and clusters. However, this motion is extremely slow when compared to familiar physical processes. The movement is governed by gravity acting over immense distances, resulting in flows that span millions or billions of years. This slow circulation contributes to the overall stillness of the cosmic environment. Observationally, the intergalactic medium is difficult to detect directly. Most of its properties are inferred through indirect measurements such as absorption lines in the spectra of distant quasars or faint emissions in specific wavelengths. These observations reveal a complex but subtle structure that would otherwise remain invisible. The difficulty in detecting this medium contributes to the perception of a silent universe where most of the material exists in forms that do not emit strong signals. Over cosmic time, the intergalactic medium evolves as galaxies continue to form, merge, and expel material. The balance between accretion and outflow shapes its composition, gradually increasing the proportion of heavier elements. However, because these processes occur over enormous timescales and across vast distances, the overall changes are slow and diffuse. The medium retains much of its primordial character, preserving conditions similar to those that existed shortly after the formation of the universe. The intergalactic medium represents a transitional environment between dense cosmic structures and complete emptiness. It contains matter, energy, and motion, yet all at levels far below those required for rapid or complex interactions. This state contributes to the broader quietness of the universe, where even the regions filled with gas remain largely inactive when viewed on cosmic scales. Within galaxies, stars are separated by vast distances that define the internal structure of stellar systems. Although galaxies appear dense when viewed from afar, their actual volume is largely empty space. Individual stars occupy only a tiny fraction of a galaxy's total region, and the distances between them are measured in light years rather than simple astronomical units. This separation creates an environment where direct interactions between stars are extremely rare, even over billions of years. Each star moves through its galactic environment under the influence of gravity, following orbits shaped by the combined mass of visible matter and dark matter. These orbits are stable over long periods, yet they rarely bring stars into close proximity. The typical distance between neighbouring stars ensures that their gravitational fields interact only weakly, preventing frequent collisions or disruptive encounters. As a result, stellar systems evolve largely in isolation, even while sharing the same galactic structure. The space between stars is filled with extremely low-density gas and dust remnants of previous stellar generations. This material forms part of the interstellar medium, which differs from the intergalactic medium in being slightly denser and more chemically enriched. Even so, it remains far too sparse to support continuous chemical activity on a large scale. Most of the volume within a galaxy is occupied by this thin medium, through which radiation and particles travel with minimal obstruction. Despite the apparent emptiness, this interstellar environment plays a critical role in the life cycle of stars. Over time, regions of higher density within molecular clouds can collapse under gravity, leading to the formation of new stars. However, these regions are localized and separated by large distances, meaning that star formation occurs in isolated pockets, rather than across the galaxy as a whole. This patchiness contributes to the uneven distribution of stellar activity. The low density of matter between stars means that collisions between gas particles are infrequent, limiting the efficiency of energy transfer. In many regions, gas remains in a diffuse state for extremely long periods, slowly influenced by shock waves from supernovae or stellar winds. These energetic events can compress surrounding material, but their effects diminish rapidly with distance, leaving large regions largely unaffected. Radiation within galaxies travels through this sparse medium with relatively little absorption. Light emitted from stars can traverse thousands of light years, carrying information about stellar composition, temperature, and motion. However, because the intervening space contains little material, there are few interactions that would significantly alter or scatter this light. This transparency contributes to the ability to observe distant regions of galaxies, while also emphasizing the emptiness that dominates their internal structure. Star clusters represent localized exceptions to this general isolation. In these regions, stars are more densely packed, sometimes separated by distances much smaller than typical galactic averages. Even so, the scale of separation remains large compared to planetary systems, and direct stellar collisions are still rare. Over time, gravitational interactions within clusters can lead to gradual changes in stellar orbits, but the overall structure remains loosely bound. Outside of clusters, most stars exist as solitary systems. The Sun, for example, travels through the Milky Way in relative isolation, with no nearby stellar neighbours close enough to significantly influence its planetary system. This isolation is typical for most stars in spiral galaxies, reinforcing the idea that galaxies are structured more by empty space than by continuous matter. The distribution of stars within galaxies is not uniform. Spiral arms, for instance, contain higher concentrations of gas dust and young stars, while other regions are more diffuse and contain older stellar populations. These variations arise from density waves that move through the galactic disk, compressing material and triggering star formation in specific regions. Even within these structures, however, the overall density remains low compared to everyday physical environments. As galaxies evolve, interactions such as mergers and tidal forces can redistribute stars and gas, altering their internal structure. Despite these dynamic processes, the vast distances between stars ensure that the overall system remains dominated by emptiness. Even during galactic collisions, individual stars are unlikely to collide directly, as the scale of separation is too large for frequent contact. The quiet nature of stellar environments contributes to the broader silence of the universe. Most energy within galaxies is emitted by individual stars or compact objects, while the spaces between them remain largely inactive. This imbalance between localized activity and widespread emptiness defines the internal character of galaxies across cosmic time. Within the quiet structure of galaxies, stars originate from large clouds of gas and dust known as molecular clouds. These clouds are among the coldest and densest regions in interstellar space, yet they remain extremely diffuse compared to any environment on a planetary scale. Their temperatures are low enough for simple molecules to form particularly molecular hydrogen, which dominates their composition. Over long periods, gravity gradually shapes these clouds into regions of varying density, setting the stage for star formation. The internal structure of molecular clouds is far from uniform. Instead of smooth distributions, they contain clumps, filaments, and irregular density variations. These variations arise from a combination of turbulent magnetic fields and external influences such as shock waves from nearby supernovae. Despite this complexity, most of the cloud remains inactive, with only small regions reaching conditions necessary for gravitational collapse. The majority of the material stays dispersed, contributing to the overall quietness of the galactic environment. When a region within a molecular cloud becomes sufficiently dense, gravity begins to dominate its evolution. The gas starts to contract, slowly drawing surrounding material inward. As the contraction continues, the central region becomes increasingly compact and opaque, preventing radiation from escaping easily. This marks the early stage of protostar formation. However, even at this point, the process is slow and gradual, occurring over long timescales that span thousands to millions of years. The collapse of gas is not uniform. Different regions within the same cloud may evolve independently, leading to the formation of multiple protostars within a single molecular structure. These forming stars remain embedded in dense envelopes of gas and dust, making them difficult to observe directly. Most of their energy is released in infrared wavelengths as heat slowly escapes through surrounding material. Despite this internal activity, the broader cloud remains largely unchanged. Magnetic fields play a subtle but important role in regulating the collapse process. They provide resistance to compression, influencing the rate at which gas can condense. In some regions, magnetic pressure can slow or even temporarily halt collapse, maintaining equilibrium for extended periods. This balance between gravity turbulence and magnetic forces contributes to the fragmented nature of star formation, where only certain areas proceed towards stellar birth, while others remain stable. As protostars evolve, they accumulate mass from their surrounding environment. This accretion process is inefficient and uneven, with material falling inward along preferred directions shaped by angular momentum. As a result, rotating disks often form around young stars. These disks contain the remaining gas and dust from the original cloud, distributed in flattened structures that may eventually lead to planet formation. However, most of the disk material is eventually either incorporated into the star or dispersed back into space. The energy released during early stellar formation affects the surrounding cloud. Outflows and jets can emerge from the poles of protostars, injecting energy into nearby regions and dispersing some of the surrounding gas. These processes help regulate star formation by preventing all nearby material from collapsing at once. Even so, their influence remains localized, and large portions of the molecular cloud remain unaffected. Despite the dynamic processes occurring within them, molecular clouds occupy only a small fraction of a galaxy's volume. Most of the interstellar space remains devoid of dense material, reinforcing the overall quiet structure of the galaxy. Star formation is therefore a localized phenomenon occurring in isolated pockets, rather than across continuous regions. This spatial limitation contributes to the broader sense of inactivity across cosmic scales. Over time, newly formed stars begin to influence their surroundings more strongly. Radiation pressure, stellar winds, and eventual supernova explosions reshape nearby gas, dispersing or compressing material depending on local conditions. These feedback processes gradually alter the structure of the molecular cloud, often leading to its partial or complete dissipation. However, this transformation occurs over extended timescales, allowing large regions of the cloud to remain stable for long periods. The life cycle of molecular clouds is therefore cyclical. They form from the accumulation of interstellar gas, evolve through phases of internal structure and star formation, and eventually disperse back into the galactic medium. Despite this cycle, the overall efficiency of star formation remains low, meaning that most of the material in galaxies never becomes part of stars. This inefficiency contributes to the persistent quietness of the universe, where active processes are confined to limited regions. Within the broader galactic environment, molecular clouds represent the primary sites of complexity and change. Yet even here, activity is localized, slow, and constrained by physical conditions. The vast majority of space surrounding these clouds remains empty, emphasizing the contrast between regions of creation and the surrounding silence that dominates cosmic structure. Within planetary systems, matter becomes organized into tightly bound structures, governed by the gravity of a central star. Planets, moons, asteroids, and smaller bodies all orbit within a shared gravitational environment, yet the space between them remains vast. Even in systems with many planets, the volume occupied by solid or gaseous bodies is extremely small compared to the empty space that separates them. This separation defines the internal quietness of planetary systems, where motion exists but direct interaction is rare. A typical planetary system forms from a rotating disk of gas and dust surrounding a young star. This protoplanetary disk gradually evolves as particles collide and stick together, forming larger and more complex structures. Over time, these structures become planetesimals, then protoplanets, and eventually full planets. However, this process is inefficient, with most of the original material either accreted by the star or dispersed into space. As a result, the final system contains only a small fraction of the mass that once existed in the disk. The distribution of planets within a system is highly uneven. Some regions contain large gas giants, while others contain smaller rocky worlds or remain largely empty. Between these bodies, vast distances dominate, filled only by sparse dust and occasional streams of particles. These regions are dynamically stable, meaning that material can remain in orbit for billions of years without significant change, yet they are also physically inactive with little ongoing interaction. Asteroid belts and debris fields represent areas of increased density within planetary systems, but even these regions are extremely diffuse. Individual objects are separated by distances so large that collisions are rare on human timescales. When collisions do occur, they tend to produce smaller fragments rather than large-scale restructuring. This contributes to a slow and gradual evolution of these regions, where change is present but limited in scope. The gravitational influence of the central star dominates the structure of the system. Its mass determines orbital speeds and distances, creating stable paths for planets and smaller bodies. These orbits are largely predictable and persistent, allowing systems to remain stable over billions of years. Despite this stability, the interactions between objects are minimal, reinforcing the sense of isolation within the system. Radiation from the central star fills the system with light and energy, yet most of space remains empty of matter. This radiation travels unimpeded across vast distances, interacting only weakly with dust or gas. The result is a bright but sparse environment where energy is present but physical interaction is limited. Planets receive this radiation unevenly depending on their distance and atmospheric composition, but the surrounding space remains largely unchanged. Planetary atmospheres introduce localized complexity containing layers of gases with varying temperature, pressure, and composition. However, these atmospheres are confined to individual planets and do not significantly affect the surrounding system. Outside these boundaries, space remains a near vacuum with particle densities far lower than any atmospheric layer. This sharp transition between planetary environments and interplanetary space reinforces the overall emptiness of the system. Comets and long-period objects travel through the outer regions of planetary systems, often originating from distant reservoirs such as Oort clouds. Their orbits carry them through vast distances of empty space before briefly entering the inner system. These journeys highlight the scale of separation within planetary environments, where even active objects spend most of their time in isolation. Over time, gravitational interactions between planets can slowly reshape orbital configurations. These changes occur over millions or billions of years and are often subtle, involving small shifts in orbital shape or position. In rare cases, stronger interactions can lead to collisions or ejections, but most systems remain stable and quiet throughout their lifetimes. The overall structure of a planetary system is therefore defined by balance and emptiness. While gravitational forces maintain order and motion, the lack of frequent interactions ensures that systems remain largely inactive. Planets continue their long orbits in isolation, separated by distances that far exceed their physical sizes. This separation contributes to the broader cosmic pattern of quietness, where structure exists but interaction is minimal. Within this framework, planetary systems represent a middle scale between the dense activity of stars and the vast emptiness of interstellar space. They contain complexity and motion, yet they remain overwhelmingly empty, reinforcing the dominant characteristic of the universe. As a whole, vast regions of space with limited direct interaction between structures. Within the narrow region around a star where temperatures allow liquid water to exist on a planetary surface, a zone of potential habitability emerges. This region is defined by the balance between incoming stellar radiation and the ability of a planet to retain heat through its atmosphere and surface properties. The position of this zone varies depending on the luminosity and stability of the star, but it remains a relatively thin band within the much larger structure of a planetary system. Even within this region, conditions are not guaranteed to support stable environments, as many additional factors influence surface and atmospheric behavior. The concept of habitability depends strongly on the presence and composition of an atmosphere. A sufficiently thick atmosphere can distribute heat across a planet, reducing temperature extremes between day and night. It can also regulate surface conditions through greenhouse effects which trap and redistribute thermal energy. However, if an atmosphere is too thin or too dense, it can prevent stable liquid water from forming. This delicate balance is difficult to achieve and maintain over long periods, making stable habitability a rare outcome even within the correct orbital range. Planetary surfaces within habitable zones vary widely depending on their geological and atmospheric histories. Some may develop stable oceans while others remain dry or frozen, despite receiving similar levels of stellar energy. The presence of liquid water depends not only on temperature but also on atmospheric pressure and chemical composition. Over time, geological processes such as volcanism and tectonic activity can influence atmospheric conditions, slowly altering a planet's capacity to support stable surface liquids. Stellar variability introduces additional complexity. Stars are not constant sources of energy, and their output can change over time due to magnetic activity, internal processes, or evolutionary stages. Even small variations in radiation can have significant effects on planetary climates. These fluctuations can lead to long-term changes in surface conditions, potentially destabilizing environments that were once within habitable limits. Despite this, many systems remain stable for long periods, allowing planets to exist within consistent thermal ranges. The distribution of energy across a planet's surface is also influenced by rotation and axial tilt. A rapidly rotating planet can distribute heat more evenly, while a slowly rotating one may experience extreme temperature differences between illuminated and dark regions. Axial tilt introduces seasonal variations which can further complicate climate stability. These factors interact with atmospheric circulation patterns, creating complex systems that determine local and global environmental conditions. Even within a habitable zone, most space remains empty and inactive. Planets occupy only small fractions of the available orbital region, and the distances between them remain vast. The habitable zone itself is not a continuous region of activity, but a spatial condition defined by energy balance. Within it, most locations remain unoccupied, reinforcing the overall emptiness that characterizes planetary systems and the broader universe. The potential for chemical complexity increases within habitable zones due to the presence of liquid solvents and stable energy sources. Chemical reactions can occur more readily under these conditions, allowing for the gradual formation of increasingly complex molecules. However, this process is highly dependent on local conditions and does not occur uniformly across all planets within the zone. Many environments remain chemically inactive despite being located within the correct orbital range. The persistence of habitable conditions over time is another critical factor. A planet may enter or leave the habitable zone as its star evolves, or as orbital parameters shift. This means that habitability is often temporary on cosmic timescales. Even when conditions are favorable, they may not remain stable long enough for significant long-term development. This temporal limitation adds another layer of rarity to environments capable of sustaining complex chemistry. Within this narrow region of potential stability, interactions between atmosphere, surface, and stellar radiation create dynamic but localized systems. These systems operate independently from the broader galactic environment, which remains largely unaffected by their presence. As a result, habitable zones represent isolated pockets of complexity within an overwhelmingly empty and quiet cosmic structure. The rarity of stable conditions contributes to the overall silence of the universe. Even though many stars exist, only a small fraction possess planetary systems with suitable orbital configurations, and an even smaller fraction maintain long-term stability. This combination of spatial and temporal constraints limits the number of environments where complex processes can develop and persist. As a result, habitable zones stand as narrow and fragile regions within the vast emptiness of space. They represent areas where energy, matter, and time align in rare configurations, yet they remain embedded within a universe dominated by separation and distance. This contrast between localized potential and universal emptiness reinforces the broader pattern of cosmic quietness that defines large-scale structure. The detection of planets outside the solar system relies on indirect methods that reveal their presence through subtle effects on light and motion. Because these worlds are extremely distant and do not emit their own visible light, they cannot be observed directly in most cases. Instead, their existence is inferred by measuring changes in the brightness or position of their host stars. These changes are often extremely small, requiring precise and continuous observation over long periods. One common method involves monitoring periodic dimming of a star's light when a planet passes in front of it. This event, known as a transit, causes a slight reduction in observed brightness that repeats at regular intervals if the planet's orbit is stable. The depth and duration of this dimming provide information about the planet's size and orbital period. However, the alignment required for such observations is rare, meaning only a small fraction of planetary systems can be detected in this way. Another method relies on measuring the gravitational influence of a planet on its star. As a planet orbits, it causes the star to move slightly in response, creating small shifts in the star's spectral lines due to the Doppler effect. These shifts indicate motion toward or away from an observer, revealing the presence of an unseen companion. This technique is sensitive to larger planets and closer orbits, but becomes increasingly difficult to apply for smaller or more distant worlds. Direct imaging of exoplanets is possible in limited cases, typically when planets are large, young, and far from the glare of their host stars. Even in these situations, advanced instruments are required to block out stellar light and isolate faint planetary emissions. The resulting images provide valuable information but represent only a small subset of known planetary systems. Most planets remain invisible even to the most sensitive telescopes. The limitations of detection methods contribute to an incomplete understanding of planetary populations. Many planets likely exist that remain undetected due to size, distance, or orbital orientation. This observational bias means that current catalogues represent only a fraction of the true diversity of planetary systems. As a result, statistical estimates must be used to infer the broader distribution of planets across the galaxy. Signal noise presents another challenge in exoplanet detection. Stellar activity such as flares, spots, and oscillations can mimic or obscure planetary signals. These natural variations in stellar behavior introduce uncertainty into measurements, requiring long-term data collection and careful analysis. Even with advanced techniques, distinguishing planetary effects from stellar noise remains a complex task. The vast distances involved further complicate detection efforts. Light from distant stars takes many years to reach observation points, meaning that data represents conditions from the distant past. This time, delay limits the ability to observe dynamic changes in real time, reinforcing the slow and static nature of astronomical observation. The universe appears not only distant but temporally separated from direct experience. Despite these challenges, thousands of exoplanets have been identified across a wide range of stellar environments. These discoveries reveal a surprising diversity in planetary sizes, compositions, and orbital configurations. Some systems contain tightly packed planets, while others show wide separations and irregular orbits. However, even with this diversity, most systems remain fundamentally characterized by large empty spaces between planets. The difficulty of detection contributes to the broader perception of a quiet universe. Many planetary systems likely exist without producing detectable signals strong enough to reach current instruments. Their presence remains hidden within the limitations of observational technology, leaving vast regions of space effectively silent from an informational perspective. What is not detected appears absent even when it is physically present. Over time, improvements in observational technology continue to increase the sensitivity of detection methods. More subtle signals can be identified, and smaller planets can be observed at greater distances. However, even with these advancements, the fundamental challenge remains the same: the vastness of space and the faintness of signals across interstellar distances. Exoplanet detection therefore operates at the boundary between presence and invisibility. It reveals that planetary systems are likely common, yet also emphasizes how little of the universe can be directly observed. The majority of space remains beyond the reach of current methods, reinforcing the idea that cosmic structures exist largely in silence from an observational standpoint. Within this framework, the universe appears not only physically vast but also informationally sparse. Signals are rare, weak, and often indistinguishable from background noise. This reinforces the broader pattern established across cosmic scales, where structure exists but interaction and detectability remain limited by distance and scale. Electromagnetic radiation forms the primary channel through which information travels across the universe, carrying light, radio waves, and other forms of energy through vast distances. This radiation moves at a constant speed in a vacuum, yet its intensity decreases as it spreads outward from its source. Over interstellar and intergalactic scales, this spreading causes even powerful emissions to become faint and difficult to distinguish from background noise. As a result, most signals lose clarity long before reaching distant regions of space. Light emitted by stars carries detailed information about their composition, temperature, and motion. However, as this light travels through space, it undergoes gradual redirection and dilution. The expansion of the universe stretches its wavelength, reducing its energy and shifting it toward lower frequency forms. This process, known as cosmological redshift, is not caused by motion through space alone, but by the expansion of space itself. Over extreme distances, this stretching can render originally visible light into infrared or radio wavelengths that are far more difficult to detect. The inverse square law governs the reduction in signal strength as radiation spreads. As distance increases, the same amount of energy is distributed over a larger area, causing intensity to decrease rapidly. Even small increases in distance result in significant reductions in signal strength. In cosmic terms, this means that light from distant galaxies becomes extremely weak by the time it reaches observational instruments, often requiring long exposure times or highly sensitive detectors to capture. Intervening matter also affects the propagation of electromagnetic radiation. Although interstellar and intergalactic space is largely empty, it still contains sparse gas and dust particles. These particles can absorb or scatter specific wavelengths of light, creating subtle distortions in the observed signal. In some cases, this leads to absorption lines that reveal the presence of specific elements along the path of travel. However, most radiation passes through without significant alteration, emphasizing the transparency of large regions of space. Radio waves, which have longer wavelengths, can travel through space with relatively little interference. However, even these signals weaken over distance and eventually blend into background cosmic radiation. Natural sources such as pulsars and quasars produce strong radio emissions, but by the time these signals reach extreme distances, they become indistinguishable from general noise. Artificial signals, if they exist, would face the same limitations, gradually losing strength and clarity as they expand outward. The cosmic microwave background represents the oldest form of electromagnetic radiation in the universe. It fills all of space with a nearly uniform glow, originating from the early stages of cosmic expansion. This background radiation provides a baseline level of noise against which all other signals must be detected. Its presence ensures that even in the absence of stars or galaxies, space is never completely dark or silent in an electromagnetic sense. The interaction between radiation and cosmic expansion creates a gradual fading of information over time. Signals emitted billions of years ago are now stretched and weakened to the point where they carry only minimal information. This loss of detail contributes to the observational limits of astronomy, where only a fraction of the universe's history can be directly accessed through light. Despite these limitations, electromagnetic radiation remains the most important tool for exploring cosmic structure. It allows observations of distant galaxies, star formation regions, and planetary systems. However, the same properties that make it useful also impose strict limits on how far and how clearly information can travel. The combination of distance expansion and dispersion ensures that most signals become progressively weaker as they move outward. Within galaxies, electromagnetic radiation interacts more frequently with matter than in intergalactic space. Dust clouds can obscure visible light, while dense regions can absorb or re-emit energy in different forms. This creates complex patterns of brightness and shadow that reveal the structure of galaxies but also limit observational clarity. Even within relatively dense environments, large regions remain hidden or only partially visible due to these interactions. The weakening of signals across space contributes directly to the perception of a quiet universe. Although energetic events occur constantly across cosmic scales, their signals are often diluted before reaching distant observers. This means that the observable universe represents only a filtered and weakened version of its true activity. Much of what occurs remains undetectable due to the limits imposed by distance and expansion. Over long timescales, the continued expansion of space will further stretch and weaken all electromagnetic signals. Distant sources will eventually fade beyond detectability, leaving only nearby structures observable. This gradual fading reinforces the long-term trend toward observational silence. where fewer signals remain strong enough to be distinguished from background radiation. The propagation of electromagnetic waves therefore defines both the connection and the separation between regions of the universe. It allows information to travel across vast distances, yet it also ensures that this information becomes increasingly faint. In this way, the universe maintains a balance between communication and silence, where signals exist but are continually reduced by the structure of space itself. Within the broader electromagnetic environment of the universe, a persistent background of radio emission forms from a combination of natural and diffuse sources. This background is not uniform in origin, but it appears nearly uniform in observation, due to the immense distances and overlapping signals involved. It includes contributions from distant galaxies, energetic astrophysical objects, and weak emissions that have been stretched and diluted by cosmic expansion. As these signals accumulate, they form a low-level haze of radio energy that fills space in all directions. Natural radio sources such as pulsars, quasars, and active galactic nuclei produce some of the most powerful emissions in the universe. Pulsars emit highly regular pulses of radio waves due to their rapid rotation and strong magnetic fields, while quasars generate intense radiation from matter accreting onto supermassive black holes. Despite their strength at the source, these signals diminish significantly over intergalactic distances. By the time they reach distant observers, their structure is often degraded, blending into background levels that are difficult to distinguish from other weak emissions. As electromagnetic signals travel outward, they expand through space and lose intensity according to geometric spreading. This process ensures that even highly focused emissions become diffuse over time. The further a signal travels, the more it blends into the general background of cosmic radiation. In regions far from strong sources, this results in an environment where individual signals are no longer clearly separable, contributing to a sense of uniform quietness in the radio spectrum. The cosmic radio background is also influenced by the cumulative effect of countless unresolved sources. Many distant galaxies emit weak radio waves that, when combined, form a diffuse background signal. Individually, these emissions are too faint to detect, but together they contribute to a persistent low-level radiation field. This field is not dominated by any single source, but instead reflects the integrated history of cosmic activity across billions of years. Intervening matter plays a subtle role in shaping radio propagation. Although space is largely empty, sparse ionized gas can affect the travel of low-frequency waves. These interactions may cause slight delays, scattering, or dispersion of signals, particularly over long distances. However, because the density of this medium is extremely low, most radio waves pass through without significant alteration, preserving the overall structure of the background field. In addition to astrophysical sources, the cosmic microwave background provides a dominant component of electromagnetic noise at microwave frequencies. This radiation is a remnant of the early universe, now cooled and stretched by expansion. It forms a nearly uniform background that permeates all of space, serving as a baseline against which other signals must be measured. Its uniformity reflects the early conditions of the universe, when matter and radiation were closely coupled. The presence of multiple overlapping radiation fields creates a complex but faint electromagnetic environment. While energetic events continue to occur throughout the universe, their signals are superimposed on this background, making them increasingly difficult to isolate at large distances. The result is a layered structure of emissions where strong local signals are surrounded by weaker, more diffuse radiation that fills all space. Over time, the expansion of the universe further stretches these signals, reducing their energy and shifting their frequency toward lower values. This gradual redshifting causes many emissions to drift out of detectable ranges, effectively removing them from observational access. As a consequence, the observable radio universe becomes progressively quieter as signals lose strength and coherence. Within galaxies, localized radio sources remain detectable due to their relative proximity and intensity. However, even within these environments, background noise from diffuse emissions can complicate detection. The separation between meaningful signals and background radiation becomes increasingly subtle, requiring advanced instrumentation and long observation periods to distinguish between them. The accumulation of weak signals across cosmic history creates a persistent but understated layer of electromagnetic activity. This layer does not dominate any region of space, yet it is always present, forming a constant background against which all other phenomena occur. It reflects the combined output of countless distant sources, each contributing a small fraction to the overall field. Despite this continuous emission, the universe appears quiet at large scales, because individual signals are rarely strong enough to stand out across extreme distances. The combination of expansion, geometric spreading, and background overlap ensures that most radiation becomes indistinguishable from the general noise floor. This limitation defines the observable boundary of electromagnetic communication across space. The radio background therefore represents both connectivity and obscurity. It carries the imprint of cosmic activity while simultaneously masking individual sources. This dual nature contributes to the broader perception of a silent universe, where activity exists but is diluted into a nearly uniform background that reveals only faint traces of its origins. Within the framework of observational astronomy, the detection of technological activity beyond Earth relies on the search for subtle patterns embedded in natural cosmic signals. These patterns, often referred to as technosignatures, are not direct observations of technology, but inferred possibilities based on anomalies in radiation structure or timing. Because the universe is dominated by natural astrophysical processes, distinguishing artificial patterns from natural ones requires extreme precision and long-term stability in measurement. One potential class of technosignatures involves narrow-band radio emissions that differ from typical astrophysical sources. Natural objects tend to produce broad or variable frequency ranges, while artificially generated signals in theory could appear more structured or confined. However, many natural processes can also produce narrow-band emissions under specific conditions such as pulsars or molecular transitions in interstellar gas. This overlap makes interpretation difficult, as similar signals may arise from entirely different physical origins. Another possible indicator involves repeated or highly regular timing patterns in received signals. Periodicity can occur naturally through rotating neutron stars or orbital dynamics, but it can also resemble engineered communication structures. The challenge lies in separating naturally occurring periodicity from patterns that might indicate intentional modulation. In practice, observational data often require extensive filtering and statistical analysis to determine whether any pattern deviates significantly from expected astrophysical behavior. Infrared excess around stars has also been considered as a potential technosignature. This concept involves the detection of waste heat that might be produced by large-scale energy usage. However, natural sources such as dust disks or star formation regions can also generate similar infrared emissions. The ambiguity between natural and hypothetical artificial sources highlights the difficulty of interpreting large-scale observational data in a universe dominated by energetic natural phenomena. The search for technosignatures is further complicated by distance and signal degradation. Any emissions originating from distant systems must travel across vast stretches of expanding space before reaching observers. During this journey, signals become weaker, redshifted, and increasingly difficult to distinguish from background radiation. This means that even if structured signals exist, their detectability decreases rapidly, with distance reinforcing the observational quietness of the cosmos. Statistical approaches are often used to assess the likelihood of non-random patterns in astronomical data. These methods compare observed signals against models of expected natural variation. However, because the universe contains a wide range of dynamic and complex processes, natural variability itself can produce patterns that resemble structured signals. This overlap creates a fundamental uncertainty in distinguishing between chance and design. The vast number of stars in the galaxy suggests that planetary systems are common, yet the absence of confirmed technosignatures raises questions about detectability rather than existence. It remains possible that signals exist but are too weak, too rare, or too dispersed to be reliably identified with current technology. Alternatively, they may exist in forms that do not resemble patterns humans are capable of recognizing. Interstellar distances introduce additional limitations. Even if a signal is transmitted with high power, it spreads across an expanding sphere of space, reducing its intensity dramatically. By the time it reaches another star system, it may be indistinguishable from background noise. This geometric dilution ensures that most signals, regardless of origin, fade into the general electromagnetic environment of the galaxy. The time delay between emission and observation further complicates interpretation. Signals from distant sources represent conditions from the past, sometimes millions or billions of years earlier. This temporal separation means that even if a technosignature were detected, it would reflect an ancient state rather than a current one. The universe therefore appears not only spatially vast but also temporally disconnected. Within this context, the absence of clear technosignatures contributes to the broader perception of cosmic silence. The lack of identifiable artificial signals does not necessarily indicate absence of activity, but rather highlights the limitations of detection across extreme distances and timescales. The observational boundary defines what can be known, leaving much of the universe beyond direct interpretation. Even within the solar system, continuous monitoring has not revealed persistent structured signals originating from non-natural sources. Instead, all detected emissions are consistent with known astrophysical or human-generated origins. This reinforces the idea that detectable technological activity, if it exists elsewhere, may be extremely rare or difficult to observe from distant vantage points. The search for technosignatures continues to expand with improved instrumentation and broader observational coverage. More sensitive arrays and longer observation baselines increase the likelihood of detecting faint or unusual signals. However, the fundamental constraints of distance, energy, dispersion, and background noise remain unchanged. These constraints define the limits of what can be observed regardless of technological progress. In this environment, the universe maintains a state of apparent silence, not because activity is absent, but because signals are diluted, ambiguous, or beyond detection thresholds. The combination of physical laws and observational limits shapes a cosmos where information is present but rarely accessible in clear form, reinforcing the perception of a quiet and isolated cosmic environment. Across cosmic time, the emergence of life depends on a sequence of chemical conditions that gradually increase molecular complexity. In interstellar space, simple molecules form within cold clouds of gas and dust, where atoms combine through slow and rare interactions. These environments contain hydrogen, carbon, oxygen, nitrogen, and other basic elements distributed in extremely low densities. Although reactions are infrequent, the vast timescales involved allow a wide variety of molecular structures to develop. Within molecular clouds, ultraviolet radiation from nearby stars can drive chemical changes by breaking and reforming bonds. This energy input allows the formation of more complex organic molecules on the surfaces of dust grains, where atoms can accumulate and interact more efficiently than in free space. Over time, these grains become coated with layers of ice and organic compounds, creating a chemically rich but physically sparse environment. Despite this richness, the overall activity remains extremely slow compared to any planetary process. As molecular clouds evolve, regions of higher density can collapse to form stars and planetary systems. During this process, complex molecules may be incorporated into forming planets, delivering pre-existing chemical diversity to new environments. However, the distribution of these molecules is uneven, and many regions may lack the necessary conditions for further chemical evolution. This unevenness contributes to the rarity of environments where chemistry can proceed toward higher complexity. On planetary surfaces, liquid solvents such as water can provide a medium for sustained chemical reactions. Within such environments, molecules can interact more frequently, allowing chains of reactions to develop over time. Temperature, pressure, and chemical availability all influence the stability of these processes. Even under favorable conditions, the progression from simple molecules to more complex self-organizing systems requires a long sequence of rare events. Energy sources such as stellar radiation, geothermal heat, and chemical gradients can drive non-equilibrium chemistry. These energy flows maintain systems away from equilibrium, allowing complexity to emerge gradually. However, the balance between stability and energy input is delicate. Too much energy can destroy emerging structures, while too little can halt chemical progression entirely. This narrow range of conditions contributes to the limited distribution of complex chemical systems. In many planetary environments, chemical evolution may stall at intermediate stages. Molecules may form and break apart repeatedly, without reaching stable self-sustaining configurations. This creates a landscape where chemical activity exists, but does not progress beyond basic complexity. Such environments remain dynamically active at microscopic levels, yet they lack long-term structural development. The transition from non-living chemistry to self-replicating systems is not well understood in detail, but it is believed to require a combination of molecular stability, environmental persistence, and energy flow. These requirements must align over extended periods, which may be rare even in suitable planetary conditions. The difficulty of maintaining all necessary factors simultaneously contributes to the uncertainty surrounding the emergence of life. Once self-replication begins, chemical systems can evolve through variation and selection, gradually increasing in complexity. However, this process is highly dependent on environmental stability. Sudden changes in temperature, radiation, or chemistry can disrupt or reset developing systems. As a result, long-term continuity is essential for sustained progression. The distribution of potentially habitable environments across the galaxy is influenced by many factors, including stellar-type planetary composition and orbital stability. Even if suitable conditions exist, they may be separated by vast distances and long timescales. This spatial and temporal separation reduces the likelihood of interaction or convergence between developing systems. Within the broader cosmic environment, chemical evolution remains a localized phenomenon. It occurs in isolated pockets where conditions briefly align, while the majority of space remains chemically inactive or too diffuse for sustained reactions. This uneven distribution reinforces the overall quietness of the universe, where complex processes are rare and scattered. The formation of complexity therefore depends on a sequence of increasingly specific conditions, each narrowing the range of possible environments. From interstellar chemistry to planetary surfaces, each step reduces the number of suitable locations. This progressive filtering contributes to the rarity of advanced chemical systems across cosmic scales. Even in environments where chemistry becomes highly active, the surrounding space remains unchanged. Chemical evolution does not significantly alter the large-scale structure of galaxies or interstellar space. Instead, it remains confined to small regions embedded within vast emptiness, reinforcing the contrast between localized activity and universal silence. Across planetary environments where complex chemistry can persist, the timescale of change becomes a defining factor in whether stable systems can develop. Planetary histories unfold over billions of years, shaped by gradual shifts in atmosphere geology and energy input from parent stars. These long durations allow for slow transformations, yet they also impose limits as environmental conditions may shift beyond suitable ranges before complex processes fully stabilize. The evolution of planetary surfaces is driven by internal and external forces. Internally, heat from radioactive decay and residual formation energy powers geological activity such as volcanism and tectonics. These processes recycle material between surface and interior layers, continuously reshaping the chemical and physical environment. Externally, radiation from the star and impacts from surrounding debris introduce additional changes, occasionally resetting local conditions through large-scale disturbances. Atmospheric composition plays a central role in regulating surface stability. Over time, gases can be added through volcanic outgassing or removed through chemical reactions and escape into space. This balance determines surface pressure and temperature, which in turn influence the stability of liquid solvents and chemical reactions. Even small shifts in atmospheric composition can produce significant changes in surface conditions over long periods. Planetary climates are influenced by feedback mechanisms that can either stabilize or destabilize environmental conditions. For example, increased surface temperature may enhance atmospheric water vapor, which can further trap heat and amplify warming. Conversely, cloud formation or chemical sequestration may reduce temperature and stabilize conditions. These feedback loops operate over extended timescales, contributing to gradual but sometimes irreversible transitions in planetary states. Orbital variations also affect long-term environmental stability. Changes in orbital shape, axial tilt, or rotational speed can alter the distribution of energy across a planetary surface. These variations occur over long cycles and can lead to periodic changes in climate patterns. While some systems remain stable under such variations, others may experience long-term shifts that reduce their suitability for sustained chemical evolution. The internal structure of a planet influences its ability to maintain long-term stability. A geologically active interior can regulate atmospheric composition and surface recycling, while a geologically inactive one may lead to atmospheric loss or stagnation. The presence of a magnetic field can also protect atmospheres from stellar wind erosion, preserving surface conditions over extended periods. These factors combine to determine how long a planet remains within a stable range of conditions. Even in stable planetary environments, chemical and physical processes remain localized. Oceans, atmospheres, and crustal systems interact continuously, but these interactions are confined to individual planets. Beyond these boundaries, space remains largely unaffected, reinforcing the separation between active regions and the surrounding emptiness of the planetary system. Over long timescales, planetary systems themselves evolve. Gravitational interactions between planets, moons, and smaller bodies can slowly alter orbital configurations. These changes are typically gradual, but they can lead to significant restructuring over billions of years. In some cases, systems become more stable as interactions settle into equilibrium. In others, they become more chaotic, leading to orbital rearrangements or the loss of smaller bodies. The lifespan of stable planetary conditions is therefore finite. Stars evolve over time, changing their luminosity and spectral output. As a star ages, its habitable region shifts, potentially moving planets out of stable zones. This gradual transformation means that even long-lived systems eventually experience environmental changes that alter their internal dynamics. Within the broader galactic environment, these processes remain isolated. Each planetary system evolves largely independently, with minimal influence from neighboring systems due to the vast distances between them. This isolation ensures that changes occur locally rather than propagating across the galaxy, reinforcing the fragmented nature of cosmic evolution. Despite the presence of dynamic processes, the overall structure of planetary systems remains dominated by empty space. Planets and other bodies occupy only a small fraction of available volume, while most regions remain unfilled. This imbalance ensures that even active systems appear quiet when viewed from large distances, as most of their structure consists of unoccupied space. The passage of time across cosmic scales therefore produces gradual but localized change. Systems form, evolve, and eventually transition into new states, yet these processes are separated by vast distances and long intervals. This separation contributes to the broader perception of a universe where activity exists, but is distributed sparsely across space and time. As planetary systems age, their capacity to sustain complex environments diminishes. Energy sources weaken, geological activity declines, and atmospheric conditions become less stable. Eventually, many systems settle into quiet configurations where little further change occurs. This final state reflects the long-term trend toward equilibrium and reduced activity on cosmic scales. Across the long lifetimes of stars, the energetic processes that define their structure gradually change as fuel is consumed and internal balance shifts. Stars begin their existence through gravitational collapse of gas, leading to ignition of nuclear fusion in their cores. This fusion process converts lighter elements into heavier ones, releasing energy that counteracts gravitational contraction. For most of a star's life, this balance remains stable, producing a long period of steady energy output that shapes surrounding planetary systems. As hydrogen fuel in the core becomes depleted, the internal structure of a star begins to adjust. The core contracts under gravity, while outer layers expand, leading to changes in temperature and luminosity. These transitions occur over extended timescales, during which the star remains luminous, but increasingly unstable in its internal processes. The shift from hydrogen fusion to helium fusion marks a new phase of stellar evolution, altering both energy output and structural dynamics. Within more massive stars, fusion progresses beyond helium into heavier elements through successive stages of nuclear burning. Each stage occurs under increasingly extreme conditions, with higher temperatures and pressures required to sustain reactions. This layered structure creates a complex internal environment where different elements are fused in distinct regions. However, each stage is temporary, as heavier fusion processes consume fuel more rapidly than earlier ones. Eventually, in the most massive stars, fusion reaches elements near iron. At this point, energy production through fusion becomes inefficient, as iron does not release energy when fused under normal stellar conditions. This leads to the collapse of the core, as outward pressure can no longer counteract gravity. The resulting implosion is one of the most energetic events in the universe, reshaping surrounding space through shock waves and radiation. The collapse of a stellar core can result in either a neutron star or a black hole, depending on the remaining mass. In the case of neutron star formation, matter is compressed to extreme densities where protons and electrons combine to form neutrons. This creates an environment where matter exists in a state far beyond ordinary atomic structure, with densities so high that a single teaspoon would weigh far more than any familiar material. Despite this extreme condition, neutron stars occupy very small volumes compared to their progenitor stars. Supernova explosions distribute elements into surrounding space, enriching the interstellar medium with heavier atoms formed during stellar evolution. These materials become part of future generations of stars and planets, continuing the cycle of matter across cosmic time. However, the distribution of this material remains uneven, and much of space between stars remains unaffected by these explosive events. White dwarfs represent another common endpoint of stellar evolution for lower-mass stars. These remnants no longer sustain fusion, and instead cool slowly over extremely long timescales. They remain stable due to quantum mechanical pressure, but gradually lose energy as they emit residual heat. Over vast periods they fade toward lower temperatures, contributing little to the energetic activity of their surroundings. Despite the dramatic nature of stellar evolution, most of a galaxy's volume remains unaffected at any given time. Stellar processes occur within isolated regions separated by vast distances. Even supernova explosions, while powerful, influence only localized areas of interstellar space. The majority of the galaxy remains in a relatively stable and quiet state, with little direct interaction between distant stellar events. The life cycle of stars therefore contributes to a pattern of localized intensity embedded within large-scale emptiness. Energy production, transformation and release occur in concentrated regions, while surrounding space remains largely unchanged. This imbalance reinforces the broader structure of the universe where activity is clustered and silence dominates the intervening regions. Over time, the rate of star formation gradually declines as available gas is consumed or dispersed. Fewer new stars are formed while existing stars continue their evolutionary paths towards stable or compact remnants. This long-term decline in stellar birth contributes to a reduction in overall energetic activity within galaxies. The end stages of stellar evolution mark a transition toward a quieter universe. As stars exhaust their fuel and settle into remnant states, the number of active energy sources decreases. Galaxies become increasingly dominated by long-lived remnants and diffuse material with fewer processes generating strong emissions or structural change. Within this framework, stellar evolution represents both creation and gradual quieting. It produces elements necessary for complexity, yet it also leads towards states of reduced energy output. Over cosmic timescales, this dual process contributes to the overall trend toward decreasing activity and increasing silence across the universe. On the largest timescales, the universe continues to evolve towards states of lower energy contrast and reduced activity. As stars complete their life cycles and star formation declines, galaxies gradually shift from bright active systems into quieter structures dominated by long-lived remnants. The remaining stellar populations consist mainly of cooler, longer-lasting stars, while more massive and short-lived stars have already disappeared. This gradual change alters the overall brightness and energetic character of galaxies without changing their large-scale structure. Black holes remain as one of the most extreme endpoints of stellar evolution and galactic development. Formed from the collapse of massive stars or through long-term growth in galactic centers, they represent regions where gravity dominates all other known forces at observable scales. Although they can influence nearby matter through accretion disks and energetic emissions, most black holes spend long periods in relatively inactive states. In the absence of nearby material to consume, they become quiet, effectively isolated within their environments. As galaxies age, the supply of interstellar gas available for new star formation becomes increasingly depleted. Gas is either locked into stars expelled into intergalactic space, or heated to temperatures that prevent efficient collapse. Without sufficient cold, dense material, the rate of new star formation declines significantly. This reduction gradually shifts the balance of galactic activity away from creation and toward long-term stability and decay. Over extremely long timescales, gravitational interactions continue to reshape galactic structure. Stars may slowly drift into new orbits, and some may be ejected entirely from their host galaxies through close encounters or interactions with massive objects. However, these processes occur so slowly that galaxies maintain their overall structure for vast periods of time even as internal composition changes. The expansion of the universe introduces an additional layer of separation between galaxies. Distant galaxies move away from each other over time, increasing the distances that light and information must travel. As expansion continues, some regions become effectively unreachable, as their recession speed exceeds the ability of light to bridge the growing gap. This leads to increasing isolation of galactic systems over cosmic timescales. Within this expanding framework, local gravitationally bound structures such as galaxies and clusters remain intact. However, everything outside these bound regions gradually recedes beyond observational reach. This separation contributes to a future in which fewer external signals are available, reinforcing the progressive quietness of the observable universe. White dwarfs, neutron stars, and black holes increasingly dominate the long-term composition of matter. These remnants represent the final stages of stellar evolution, persisting for extremely long durations. White dwarfs slowly cool neutron stars remain stable and less disturbed, and black holes persist until they gradually lose mass through extremely slow radiation processes. These objects define a universe that retains structure but loses active energy production. As time continues, even these remnants evolve toward lower activity states. Black holes emit extremely faint radiation over vast timescales, while isolated remnants drift through increasingly empty space. With diminishing interactions, the frequency of energetic events decreases and the overall level of detectable activity declines. The large-scale structure of the universe remains intact, shaped by dark matter and gravitational networks. However, the luminous components that once traced this structure become less prominent. Galaxies grow dimmer, star formation ceases, and only long-lived remnants remain visible sources of energy. The cosmic web persists, but its active illumination fades. The absence of detectable signals from distant regions becomes more pronounced as expansion accelerates separation. Light from remote galaxies eventually fails to reach observers, leaving only nearby structures visible. This observational narrowing reinforces the sense of silence as fewer sources contribute to the detectable environment over time. In this far future state, the universe retains matter structure and motion, but loses much of its energetic contrast. Without frequent star formation or large-scale energetic events, the observable cosmos becomes increasingly quiet. Activity continues only in isolated regions separated by vast and expanding emptiness. The Great Silence in this context emerges not from the absence of processes, but from their distribution across time and space. Energetic events exist, but they are rare, distant, and often unobservable. The structure of space itself disperses signals and separates regions of activity, ensuring that most of the universe remains beyond direct communication or detection. In the final perspective, the universe is not a static emptiness, but a slowly evolving system moving toward lower interaction and reduced detectability. Matter persists. Gravity continues to shape structure and remnants endure for immense durations. Yet the connections between regions weaken over time and the flow of information diminishes. The silence of the universe is therefore a product of scale expansion and distance. It reflects not an absence of existence, but an overwhelming separation between regions where existence remains active. Across billions of years, this separation grows, and the observable cosmos becomes increasingly quiet, not because nothing happens, but because almost everything becomes too distant to be heard.